Welcome back to the next framework in space. If you follow this channel, you know that our purpose isn't just to look at rockets or robots. It's to understand the fundamentals of modern engineering so that you can lead the transition toward a future dominated by artificial intelligence. Engineering is the language with which we write the future, and today that language has become much more complex. Today we are going to talk about the Mars launch window of October 2032. I know what many of you are thinking. If you saw the previous video, or if you've been following the news, you'll remember that this was the promised date. The date when, theoretically, we would see human boot prints on the red soil. The third window was supposed to be the one for colonization, but engineering doesn't understand marketing promises. It only understands physics and reliability. And I have to be direct with you. There are no humans on the ships departing in 2032. To understand why, and to comprehend the technological beast we are sending, we have to perform an honest autopsy of what happened in the 2030 window. In the previous video, I told you the plan: a massive fleet to build a fuel plant and habitats. On paper, it was perfect. In reality, the results we received 2 years ago, when that fleet arrived on Mars, were, to be generous, an operational disaster. Let's analyze the failures, because in engineering, failure is the most valuable data point. First, the fuel production system, the famous Sabatier process, collapsed before it even started. Of the 4 ships dedicated to this industrial plant, 2 suffered critical failures during the final landing maneuver and were rendered useless. But the worst part wasn't the landing, it was the mining. The surviving ships deployed the thermal extraction systems, the RedWater, and failed to extract a single drop of water. The ice was deeper or more mixed with perchlorates than the orbital scanners indicated. No water means no hydrogen. No hydrogen means no methane. The ships were stranded. Second, robotics. The Optimus V2s and construction rovers had improved navigation, yes, but not their fine mechanical dexterity. When they tried to deploy the hectares of solar farms needed to power the plant, the connectors filled with dust, the servo motors failed due to thermal cycling, and the task was left half done. We didn't have enough power. Third, the habitats. Of the 2 ships with Class 1 habitats, only one managed to deploy the module correctly. The other suffered a mechanical jam in the internal crane, and the habitat remained trapped inside the Starship, unusable. And to top it off, the life support system, although it lasted longer than in 2028, failed after 18 months. The seals couldn't withstand the chemical corrosion of the environment. The only thing, and I repeat, the only thing that worked perfectly was the optical laser communication system. Thanks to that, we watched in high definition as everything else failed. Faced with this scenario, there was an emergency meeting between NASA and SpaceX. It was a moment of lucidity. The human trip for 2032 was completely ruled out. They realized you can't send people to a place where the water machine doesn't work and the house breaks down. They set new requirements to authorize a crewed mission. More than 50 high-level milestones were established, but 3 stand out. 1. It is mandatory for a Starship to perform a takeoff maneuver from Mars and return to Earth orbit. We must demonstrate that return is possible. 2. We need a 100% success rate in the landings of the upcoming fleets, not a single failure. 3. The life support system must function autonomously and nominally for more than 2 Earth years. Realistically, this pushed the human mission to at least the 2037 window. But don't get depressed, because while Mars was teaching us a lesson in humility, here in the terrestrial neighborhood, something extraordinary was happening. The lunar program has been a resounding success. While we struggled with Martian dust, SpaceX managed to land humans on the moon in 2029 with the Starship HLS. Blue Origin succeeded in 2030 with their Blue Moon, and SpaceX repeated the feat in 2031 with 2 more ships. The moon has become our real-world testing ground, and there, we validated a technology that is the absolute protagonist of the 2032 window: nuclear energy. Furthermore, SpaceX's industrial capacity has reached levels bordering on science fiction. By the end of 2031, production has been standardized to the point where a complete Starship Super Heavy system rolls out of the factory every 4 days. They have 10 launch pads operational or under final construction across Florida, Boca Chica, California, and Hawaii. They are launching 3 times a week. They have deployed the Starlink V4 network, which not only provides internet, but includes satellites with edge artificial intelligence processing capabilities, creating an orbital computational cloud. They are building space stations with vast space and Axiom. It is a golden age for low-orbit infrastructure. With this industrial muscle, for the October 2032 window, we are not sending 10 ships, we are sending 16. 14 Starship version 3s and 2 of the brand new version 4s. The goal is to repeat everything that failed in 2030, but with redundant and improved systems. However, there is a critical novelty, a game-changing technology that solves the energy problem that doomed the previous mission. In this 2032 fleet, we are carrying nuclear fission reactors. I want to pause here and dedicate the core of this talk to explaining this technology. Understanding this is fundamental to understanding the future of space engineering. Until now, we depended on the sun. But on the moon, the night lasts 14 days and the temperature drops to 173 degrees below zero. Batteries to withstand that are unviable. And on Mars, dust storms can block the sun for months. Solar energy is intermittent. Civilization needs baseload, constant energy. In the mid-2000s, there was a radical strategic shift. Initially, 40-kilowatt reactors were sought. But in August 2025, a government directive, concerned about the advances of rival powers like China and Russia, ordered the stakes raised to 100 electric kilowatts, 100 kilowatts electric. To give you a reference, the Curiosity or Perseverance rovers run on radioisotope generators that provide about 110 watts. We are talking about a system 1,000 times more powerful. It's not an atomic battery, it's a pocket nuclear power plant. How does this marvel of engineering work? The heart of the system is the fuel. Forget the dangerous uranium rods from the movies. We use HALEU, which stands for high-assay, low-enriched uranium. It is uranium enriched between 5 and 20%. Powerful enough for a compact reactor, but incapable of generating a nuclear detonation, which greatly simplifies safety. But the real magic is in the encapsulation. The fuel comes in the form of trisoparticles. Imagine a poppy seed made of uranium, coated with microscopic layers of carbon and ceramics. Here is an analogy to visualize it. Think of each fuel particle as a tiny individual bunker. Even if the reactor heats up to 1,600 degrees, the ceramic bunker retains all radioactive products inside. It is intrinsically safe. If everything fails, if the cooling system disappears, the fuel doesn't melt. It simply sits there, hot but contained. Now, we have the heat. How do we convert it into electricity? This is where the engineering for the 2032 window had to make tough decisions. The 3 main companies for this project were Westinghouse, the IX Alliance, Intuitive Machines and X Energy, and Lockheed Martin. They debated 2 conversion technologies, the Stirling cycle and the Brayton cycle. Stirling engines work with pistons moved by the temperature difference. They are very efficient, but to generate 100 kilowatts, we would need many synchronized engines. That adds mechanical complexity. The winner for this high-power mission was the Brayton cycle. It is basically a jet engine, a turbine, but in a closed loop. An inert gas, like a mixture of helium and xenon, is heated in the reactor, expands moving a turbine at very high speed, and generates electricity. Why did Brayton win? Scalability. If you want more power with Stirling engines, you have to add more engines, which increases weight linearly. With a Brayton turbine, if you make it slightly larger, the power increases exponentially. For the industrial energy levels we need on Mars to manufacture return fuel, the Brayton is king. However, there is a monumental technical challenge I want you to grasp: heat rejection. On Earth, nuclear plants use rivers or cooling towers to cool down. In space, and in the partial vacuum of Mars, there is no air or water to take the heat away. There is only radiation. The reactor generates 100 kilowatts of electricity, but due to the laws of thermodynamics, it also generates about 230 kilowatts of waste heat that we have to dump. If we don't, the turbine melts. For this, the 2032 ships deploy immense radiators, over 100 square meters. The problem is that these radiators must be lightweight, foldable, and capable of surviving the dust. Liquid metal or gas circulation systems have been designed to carry heat from the reactor to these panels so they glow in the infrared and dissipate the energy into the cold of space. And there remains one final critical point: shielding. Uranium emits radiation. On Earth, we use concrete walls meters thick. On a spaceship, we cannot afford that weight. The solution is ingenious: the shadow shield. We don't wrap the entire reactor in lead, we only place a shield on one side, creating a safety cone, a radiation-free shadow behind the shield. It's like hiding from the sun behind an umbrella. As long as the habitats and electronic equipment are in the shadow, they are safe. But this implies a severe operational restriction. Rovers and future astronauts can never, under any circumstances, go around the reactor and leave that shadow cone. The base architecture must be designed around this invisible line of death. This is the technology inside one of the Starship V4s of the 2032 fleet. A nuclear reactor validated on the Moon, capable of providing power day and night, regardless of dust storms, to finally power the fuel production plants that failed last time. Now let's go back to the general mission. We have 16 ships crossing the void. 14 are conventional cargo, carrying armored and redundant versions of the robots, new RedWater water plants with drilling heads improved thanks to the lunar experience, and life support systems with new corrosion-resistant materials. But the two Starship V4s are the key. One carries the nuclear reactor, the other is empty. Yes, empty. The second Starship V4 has a single mission: land, fill its tanks with the fuel we hopefully produce this time thanks to nuclear energy, and take off. It must perform the first return takeoff in history. It won't return to Earth with cargo, it simply must reach Martian orbit and demonstrate that the Raptor engine works after 2 years on the surface, and that the methane produced in situ is of adequate quality. If that ship takes off, and if the nuclear reactor keeps the lights on for 2 years without human intervention, we will have met the requirements. This 2032 window is not for the triumphant arrival of humanity. It is the window of industrial brute force. It is the moment when we stop playing explorers to become builders of heavy infrastructure. We have traded the naive hope of 2030 for the robust nuclear engineering of 2032. The failures of the previous window hurt us, cost us billions, and delayed the dream by a decade. But they taught us that Mars does not forgive weakness in design. So, here we are. The 16 ships are on their way. The reactors are cold, waiting to activate upon touching Martian soil. The artificial intelligence of the Starlink satellites is ready to coordinate the largest logistics operation outside of Earth. And now, I ask you, the future engineers watching this, if this fleet succeeds, if we manage to master nuclear energy on another planet and bring a ship back, the path will be cleared for the December 2034 window and a possible crewed mission by February 2037. In 2034, with the energy infrastructure resolved, we will begin sending precursor systems for biology, scale greenhouses, synthesis labs, and perhaps the first test animals. Do you want us to analyze in the next video what will happen in the 2034 window and how the biological ground is prepared for humans? Are you interested in knowing how artificial intelligence will manage those greenhouses millions of kilometers away? At this moment, AGI has been achieved, and technological development is picking up incredible speed. Leave me a comment below with the phrase, Target 2034. Engineering is a path of iteration, failure, and learning. Today we learned from the failure of 2030 to build the power of 2032. Thank you for being there, learning to build the future. See you in the next video.